Thank you all for coming. My name is Barry Stahl. I'm a solution architect and developer based in Phoenix, Arizona. And thank you for inviting me to your little continent here. This is nice. It's been a great trip so far. I've been doing solution development, designing and implementing systems for customers, large, small, and everything in between for about 30 years now. I don't want to spend too much time on preliminaries, but I do want to give you some idea of who I am or what I am. And I think this next slide actually explains that better than I could actually tell you. This is my list of favorite physicists and favorite mathematicians. And just the fact that I have that list probably tells you everything you need to know about me. So I tweeted this out at one point. Please feel free to tell me who I missed, who shouldn't be there, or who should. Open for discussion. And these are the giants on whose shoulders we stand. So we will maybe see some appearances by a few of these as we go through the talk. We're here to talk about artificial intelligence. And so a talk on artificial intelligence wouldn't be complete without defining what it means. And if you were here for Barbara's talk previously, or if you know anything about the space or have heard or read anything about it, you probably realize that there has been a lot in the space of machine learning, a lot of advancements there. And I think because of all that hype, it's very easy to conflate artificial intelligence with machine learning. And the fact is, artificial intelligence is much more than just machine learning. Machine learning is one fantastic tool to implement artificial intelligence solutions, but there are other ways and other types of problems that can be solved using artificial intelligence. So we're going to talk about some of that today. So what is AI? What is artificial intelligence? Basically, it's a computational system that behaves rationally. So what does it mean to behave rationally? Well, to behave rationally, you need to make decisions. So we're talking about systems that make decisions on our behalf. And in doing so, they do it trying to make the best decision. That's what a rational decision is, one that attempts to make the best decision. It isn't always going to make the best decision because we're basing that on our best available understanding of how to solve the problem, that is our model, and our best available understanding of the state of the problem, our data. If we use the best available information and the best available model and try to make the best decision, we are acting rationally. Optionally, of course, we may also act on this decision, so we may build some automation into this. Once we've made a decision, we may act on that decision, but that is an optional piece of it. Now, artificial intelligence, or these kinds of systems, differ from, say, decision support systems in that decision support systems are designed and are very, very good at synthesizing and presenting data in ways that allow the users to make the decisions. We're taking that one step back and saying now the system will make the decision. So when we're talking about AI models, I find it helpful to categorize it into three different types of models. Okay, there are the logical models, which are fairly common. Those are anything that can be reduced ultimately to a collection of conditionals. Okay, so if ultimately you can reduce it to conditionals, like for example, a rules engine is a very literal list of conditionals, or object-oriented logic, a lot of the things that we've been building in the past, those fall into logic models. We talked about machine learning. Probabilistic and learning models are another type of tool we can use to build artificial intelligences. And we're not going to be focusing on that in this talk, but those generally result in a prediction of the best solution, a probabilistic-based solution. The type we're going to spend most of our time on today is the search and optimization space. These are solving problems based on reducing and searching efficiently a large set of solutions. And we're going to do several examples of that today. And that's where the Google OR tools are very, very efficient. Now, one of the things I point out on this slide is that one of the big concerns about probabilistic and learning models is that they require these huge data sets. They require, the more data you can give them, the better off you are. Search and optimization, on the other hand, benefits from having a data set to validate the model, but it doesn't require it up front. So if you have a situation where you don't have a lot of data beforehand, an optimization, you may want to implement an optimization solution. So what does that mean, optimization? What am I talking about here? In a nutshell, optimization is finding the best solution from all of the possible solutions to a problem by maximizing the good stuff and minimizing the bad stuff. Things that we want, we try to increase. Things that we don't want, features of the problem, maximize profit, minimize costs, those kind of things. So that's how we go about solving optimization problems. And the field of optimization, there are lots of ways to do it, but we're going to talk about optimizations that are based on constraint programming. And we're going to build on top of this. So the foundation of what we're going to talk about today is called constraint programming. That's dealing with constraints, and we'll talk a lot more about what that means. Then we'll build on top of that and go into linear programming. These are also using constraints and putting linear objectives on top of that and making linear constraints. And then we'll also solve some discrete problems where we're using mixed integer programming. So we use Boolean variables to assign discrete things, assign discrete portions of the problem. And we'll see exactly what that means here in a little while. So constraint-based optimization is what we're going to spend our time on, and that's where the Google OR tools provide an exceptional tool to help us with that. There are basically two classes of problems that we can solve with constraint-based methods. The first is feasibility problems. And that means we have to find a solution that works. But it doesn't really matter which one. Any possible solution will work. There's also optimization problems. And this is where we find the best solution that satisfies all those criteria. And we'll see real examples of this where something might be considered an optimization or a feasibility problem, but actually is better off as an optimization problem. Because it's not always obvious the difference between the two. And I like to illustrate that by using this cartoon from the great Randall Munroe of XKCD, who has cue ball here, who says his hobby is embedding NP-complete problems in restaurant orders. And so we have a menu over here, and cue ball says that based on that menu, we'd like to order $15, exactly $15.05 worth of appetizers. Okay. $15.05. Well, NP-complete, I'm not going to go into the details of what NP-complete means, but NP-complete problems have a feature that while they can be somewhat difficult to figure out, they're very, very easy to validate. So if I were to tell you that 7 bowls of mixed fruit satisfies the criteria, you could easily multiply 7 by $2.15 and say, yes, that does satisfy the criteria of $15.05 worth of appetizers. Okay. And that would be satisfying the constraint, a constraint satisfaction problem. This would be a solution for it. But if I'm the waiter, maybe I want to do an exceptional job. Or if I'm a waiter in the US, I actually want to get big tips. I might want to find a better solution, a solution that satisfies my customer better. And there may be other solutions to this. In fact, there are. There are 2 possible solutions to this problem based on that menu. There's 7 bowls of mixed fruit, or 1 mixed fruit, 2 hot wings, and 1 sampler plate. That solution may be a better solution. If you're a customer and you're saying, well, I can get 7 orders of mixed fruit, or 1 of this, 2 of that, and 1 of the other thing, that may be better for you as a customer. So if you're a waiter trying to do a better job for your customer, that may be the better solution. So what could we do? Well, we could throw in some optimizations there. We might say, hey, maybe we want to minimize the number of any single item. So we're not doing more, that we're not going to have 7 of anything. We're going to have 2 as the maximum of any one item in these 2 possible solutions. Or maximize the total number of distinct items, so get the maximum of the number of different items. Either of those two optimizations will lead you to the second solution and thus the better tip. But there's actually a third thing we can factor in here, and that's the perspective of the owner of the restaurant. If I'm the owner of the restaurant, I may actually want to factor something different in. I may want to I want to do the thing, I want to get you what gives me the most profit. But I also have something else I can do, and that is I can relax one of the constraints. I can give a discount. I have to give you at least $15.05 worth of value, but I can charge you $15.05 for anything that would otherwise cost more than that, taking it from a equal to problem to a greater than or equal to problem, giving me more possible solutions, right? So at that point, then maybe I say, maybe the best thing is, what is it, 5 salads are on sale for $3.01 instead of $3.35. If that makes me the most profit, I could do that. So we could have a constraint satisfaction problem that's just any solution works. We can add optimizations, and we can, in fact, sometimes do relaxations. And relaxations are actually going to become very important when we get into mixed integer programming. So we can offer a discount and maximize our profit. So what's a constraint? You've heard me talk about constraints a number of times now. What does that mean? Well, in simple terms, a constraint is simply a required condition. The problem has to do this thing. It is constrained to this condition. But I'm a programmer, and I like to think of things in terms of objects and entities and such. And to me, a constraint is actually an object that can do two things. It can verify feasibility, and it can prune the search space. Now, we'll see a real good example of pruning the search space coming up here in just a minute, so we'll come back to that. But verify feasibility, what does that mean? Well, basically it means that we make sure that it still satisfies the problem, and in fact that there is a solution that still satisfies the problem. So if it's not feasible, we can look at things in terms of infeasibility, okay? So if a solution, a possible solution to our problem does not satisfy one or more of the constraints, that solution is infeasible. And if the problem has no solutions that satisfy the criteria, then the problem itself is infeasible. And in order to solve that problem, we might have to relax some of the constraints so that we can get a good enough solution. Does this make sense? Any questions so far? Okay. All right, so quickly, types of constraints. The typical type of constraint is an inequality constraint. You'll see this a lot. A particular variable does not equal a value, or is less than or equal to a value, or an equation is less than or equal to value. That's the majority of the types of constraints you're going to see. We'll also today see integer constraints, which are basically the same thing except integer variables. So no, you don't have a full range of values available, as well as these special global constraints. These are really, really interesting global constraints. They take a more holistic view of the model. And these are predefined. There's about 400 of them out there now. There are resources online that can show you the deep math involved in understanding them. But the key to them is that they have to have a dedicated algorithm for solving the problems that they do, for solving them and determining the two things that they can determine, right? The feasibility and to prune the search space. Those two things have to have algorithms that will run in polynomial time. So they can't start to expand in exponential time. Otherwise, we won't be able to solve our problems in reasonable amounts of time. So the one we're going to see today is called an all-different constraint. And that means the variables that are specified in the all-different constraint have to take different values. All have to be different. They can't be the same. It's a really interesting research area. So if you're interested in that kind of math, it's the kind of thing that you might want to check out. All right, so that's constraints. The other thing we might need today is an objective. An objective is if we have a an optimization problem. We define the constraints, we add an objective to tell the solution or to tell the computer what makes a better solution. How do we define what is a better solution? So this is where we tell it maximize the good stuff, minimize the bad stuff. Okay? So we describe how to make the solution better with our objective, and we do so using an objective function. That objective function has to be in terms of our variables that we are trying to define. Okay? And we specify it as the goal relative to equation. So we want to minimize this equation or maximize this sum or what have you. Okay? Now, there can only be one objective per model, but we can combine features of the problem by creating like a score. And you can do that. You can even do things, well, like I want to make this bigger and I want to make this smaller by inverting or negating things. So you have to define things in such a way as your problem moves in the direction that you want when that score increases or decreases. That's very common. You'll do that a lot, and you'll spend a lot of effort trying to figure out how to ideally specify the score, define that objective. So, you ready for an example? Let's start in talking about constraint programming. And of course, this is René Descartes. Did you know that, maybe this was totally my failing, I didn't realize that the Cartesian coordinate system was named after René Descartes. My Latin failure, I guess. Anyways, one of the giants on whose shoulders we stand. Okay, so constraint programming. The canonical example, if you will, of constraint programming is Sudoku. Hopefully, many of you know Sudoku. For those who don't, it's a 9x9 grid which can be described, the solution to the problems can be described as 27 all different constraints. I mentioned the all different constraint, right? Where it's each of the variables have to take a different value. So if my variable possible values are 1 through 9, I can describe this Sudoku board as one all different constraint for each of the columns, one all different constraint for each of the rows, and one for each of the regions of 9 cells. 27 all different constraints. And we have to solve that problem. And we're given information up front. So we're told here are some values that we can apply. And we have to solve this puzzle. So how do we do that using constraint programming? Well, constraint programming is about looking at the solution space. So we could think about this grid as each one of these cells having the 9 possible values, right? So I've listed in each of the cells the possible values it can take. And this is a pretty big solution space. When you multiply all those out, it turns out that we're talking about the order of magnitude of number of possible solutions is 10 to the 77th. Now, 10 to the 80th, approximately, is our best estimate of the number of atoms in the universe. So this is pretty large. In fact, I like to say it's inconceivably large. And I like to say that way because not only so I get to invoke The Princess Bride, the greatest movie ever made, but also because it truly is. It is not conceivable to the human mind. If we try 1 trillion combinations per second, it still takes 10 to the 57 years to try them all. I looked at how many, if I stacked pennies to the moon, how many times would it go back and forth to the moon? And it's basically going across the known universe something like 10 to the 30th times or some ridiculous number like that. There is simply no way for us to conceive of those solution spaces. So naive solutions, brute force solutions will not work. We cannot just throw numbers at it and try every possible combination. It will never finish. We have to be smarter than that. So the smarter is constraint programming in this case. We have some information. We're given information. We're told that that second cell there is a value of 4. And we can make inferences about the other cells based on those constraints, or some of the other cells. So by knowing we have a 4 there, we know that all the remaining cells in this column and this row and this region cannot take that value 4. So we can eliminate that from the search space. We can prune those values from the search space. Magic word there, prune. By the way, I put it as a bonus question here. In this model, viewed like this, how would we know if our solution becomes infeasible? How do we know if there are no more, if our problem, we cannot solve our problem based on what we've tried? If any of these cells have no numbers remaining, exactly. If there are no values left in any one of these cells, that means we don't have a solution to our problem. We've eliminated all of the possible values for that cell. Somewhere we made a mistake, or the problem is not solvable. Yeah. So let's keep adding values. We have additional information. It gave us a bunch of numbers, so let's just keep adding them. By adding that 6 in there, now we have a number of cells here where there's 2 values, where we only have 7 possible values. And we've reduced our search space by 4 orders of magnitude. About 10,000 possible values were eliminated. But of course, we still have a long way to go. So to save time here, let's jump ahead to where all the values have been added and the search space pruned as much as we can there. And we're down to 10 to the 21st. Pretty significant reduction in search space. Still a lot of values remaining. But we're not done yet, because those who have done Sudoku before probably have recognized something, and for those who don't, I'll highlight it here. There are 4 cells in this grid that only have 1 possible value remaining. These are fixed points now. They have to take this value, otherwise our solution is infeasible, right? So we can set those values. We know they have to have those values. So we can go to the top 9 there, and we can add that in, and now reduce our solution space even further. And we can continue looping through. We've now fixed additional spaces here. And we continue this iterative process of pruning the search space, propagating those constraints, and doing so, creating those fixed points. Doing so is known as running a fixed point algorithm. So we loop through, run our fixed point algorithm to the end, and at the end of this process for this one, we see that we have only 1 possible solution. Now, constraint satisfaction problems like this are not always this simple. A lot of times you're going to get to the point where I've filled in all the information I have, and I didn't get to anywhere there's only 1 left. I've maybe got to one where there's a space where there's 2 possible values left. What do we do in that circumstance? Probably bifurcate the problem, right? We can run, even in parallel, one version of the problem where it's 1 value and one version where it's the other value, and continue and see if either or both of those solutions produce a value or if they become infeasible. All right? So, there are some very interesting search techniques aside from just running all possible solutions in parallel, because it would be easy to see how you could branch off into lots of search paths there. So searching is a very interesting field as well in this branch of mathematics. So that's constraint programming. Let's jump into how we'd use this to solve a more important problem, something maybe dealing with manufacturing. And this is George Dantzig, who mathematician, creator of the simplex algorithm that is used to do linear programming. Another of those giants. So let's talk about pottery. We got Pete, who runs a pottery shop out of his garage, so he only makes 2 products right now. I'm sure he's going to expand in the future because he's looking at his data in a valuable way, but he's asked us to help him out. He makes 2 products, a small vase and a large vase. And the small vase takes 1 ounce of clay and 1 ounce of glaze and sells for $3. And the large vase takes 4 ounces of clay and 2 ounces of glaze and sells for $9. Pete's asked us to look at it based on this amount of revenue, 24 ounces of clay, this amount of inventory, 24 ounces of clay, 16 ounces of glaze. He wants to know how much of each product can we produce, and how do we make the most revenue from the materials on hand. Now, we're going to look at revenue here to keep it simple. Profit may be a better way of looking at it, but let's keep it simple for right now and just look at revenue. So right off the bat, we can tell a few things. We know that an ounce of clay and an ounce of glaze is what it takes to make a small vase. So we are constrained by the amount of glaze that we have in inventory right now. So we can make at most 16 small vases. If we made nothing but small vases, we could make at most 16 of those, right? And the large vases are actually constrained by the amount of clay because they take 4 ounces of clay. So we could make at most 6 of those. So knowing that, we've actually bounded our search space here, right? We know you can't make less than 0 vases. So we have a bounding rectangle here at 0, 0, assuming that x is the number of small vases and y is the number of large vases. We have this search space, this bounding rectangle that holds our search space. So we know we can limit our search to within that space. And if we just try all the possibilities and see which ones cause us to exceed our amount of inventory, we get these 71 feasible points. Anything over in this space here uses too much of one or more of the inventory. These are all the valid values. Each of these dots represent a valid value. But you notice that 0, 0 is a valid value. I don't think Pete's going to want to make 0 of anything, or of either of his things. He doesn't want to make no product. He wants to produce product. So we don't have a constraint satisfaction problem here. We have an optimization problem. And this works very well when we only have 71 items. We could actually go through each of these 71 and calculate the revenue from each one and just hold the value, and say which one gives us the most revenue. That works with only 71 values. But what if this was 16 million and this was 6 billion here? I don't think we're going to ever finish if we try and just check all those values. So we have to be smarter about it. We can't use just a brute force solution. So let's look at these constraints a little bit differently. Let's look at them as equations. So if we just formulate the clay constraint into an equation. So this clay constraint is 1 times the number of small vases, because it takes 1 ounce of clay to make a small vase, plus 4 times the number of large vases, because it takes 4 ounces of clay to make the large vase. That has to be less than or equal to 24, which 24 ounces of clay was our clay inventory. Okay? So we've formulated that constraint in an equation. And we can plot that simply by finding the intercepts, doing basic math, and plot that on the graph. And we could do the same thing for the glaze constraint. It's x plus 2y is less than or equal to 16. And we get this interesting shape. And if you notice that if we just plot those 71 points again, they actually fit everywhere where it's underneath both of those constraints, which makes sense. We have to have less than both of those constraints, right? So it fits perfectly. Okay. This shape right here, this, what is it, 4-sided shape here, is called a polytope. Spelled with an E at the end for some reason. And there is some magic that occurs with the polytope, and George Danzig helped prove this. The local minima or maxima of any equation formed by these variables, by the variables x and y in this case, the local minima or maxima will always fall at one of the vertices of this polytope. So I only have 4 locations now that I have to test to see which my best value, what my maximum revenue should be. And this is true regardless of whether this is 16 or 16 million, or this is 6 or 6 billion. I still, because the shape is the same, I still only have those 4 points to test. Now we can really solve some large problems. What about if we added materials? If we added, say, some dye for the clay, or some gilding for the edges to finish the edges, what we're doing is we're adding variables. We're adding constraints. So we just make a different polytope. And what about if we add another product? What if we add an ashtray or an urn or something like that? Now we're talking about jumping out into 3 or more dimensions, right? Because we're adding another variable. If we add an urn, say, we can pull that out into the z-axis, and now we have a 3-dimensional shape. If we add another product, we now have a 4-dimensional shape, and we can't visualize it anymore. Fortunately, the computers are very good at doing that. We have to figure out where these vertices are, regardless of how many dimensions or how many variables we have. And I don't know the math that does that. I'm not that good at it. But I do know how to use a tool that will help us do that. And in this case, we're going to use the Google OR tools. But there are quite a few tools out there, and you can see a list of them. They're called solvers. They're on, there's a list of them on Wikipedia. They do the heavy lifting. And they're the things that allow us to bring these types, or to solutions to these types of problems into our artificial intelligences. There are 2 that I'm very familiar with. Gurobi is a commercial product that if you're going to do some real serious industrial work and you're you're putting your company's fortunes on the line, and you're probably going to want to use a commercial solution like Gurobi, something with support. To get started or to solve a lot of simpler problems or less commercial problems, the Google optimization tools is released under Apache license and has an active support community out there. And I highly recommend starting with this for most problems. So this Google OR tools, like I said, it's a suite of tools for solving these problems. And it comes with an open source constraint solver. So a tool that we could use to solve constraint problems, do constraint programming like we did with the Sudoku problem. It also comes with a unified interface for linear programming and mixed integer programming. And this interface is nice because you can get the OR tools built with any linear programming or mixed integer programming solvers like Gurobi. This just provides the interface for it. And so you can build your code, your AI, using this interface, starting with one of the open source optimizers, and then plug in a commercial optimizer later without having to change any of your code. Very powerful feature there. And then it also comes with both a linear and a mixed integer programming solver, as well as being able to program in others. Very, very useful for building our AIs. So how do we go about doing that? How do we solve a linear programming problem in Google OR tools? Well, the first thing we have to do is define our decision variables. What we're doing here is we're building up our model. So our decision variables are the values that are going to be determined. In the case of the Pottery example, x and y, or x1, x2, however you want to think about it. It's those 2 values that we have to solve for. We have to find the values of. We have to define our constraints. So we've already seen 2 constraints there. And those constraints have to be defined in terms of the decision variable. So we have to build equations based on using those decision variables. And then for optimization problems, we can also define the objective. We have to tell the model, here's our equation for our objective function, and whether or not we're going to minimize or maximize. So here's what it might look like to create our decision variables. So in this case, I've defined XS as the number of small vases and XL as the number of large vases. And to program that into the Google OR tools, it's just these 2 lines of code. We use the solver's makeInt variable, makeIntVar function, defining the lower bound and the upper bound, and max small is the maximum number of small vases we can make. And then we give it a name that it can use to describe it to us. When it needs to tell us, hey, this variable did this, it'll use this name. It doesn't have to match what our variable is in our code. It can. It's easier if it does, I think, but it doesn't have to. We also don't have to constrain the lower bounds and the upper bounds of our variables. We could say negative infinity to positive infinity. It's just good practice to constrain it as much as you can, whenever you can. It helps the solver out. but you could just say negative infinity to positive infinity, or 0 to positive infinity, et cetera. Making sense so far? Okay. So how do we define our constraints? Well, let's just look at that first constraint. Look at the clay constraint, which, as you recall, is xs plus 4xl is less than our clay supply. There's a little more code involved here, but not that much. And this is one place where the Gurobi optimizer, I think, has a much cleaner interface. For the Google interface, because it has to be more flexible because it's a generic interface, what they do is they use a make constraint method off the solver to constrain clay to between 0 and the clay supply. And you do have to specify this. This is what's telling it what the values are constrained to. So this is the less than or equal to 24 here. And then we have to tell it what the equation looks like. And so we do that by setting the coefficients. So we're telling it xs, that variable, participates in this constraint with a coefficient of 1. So that's the xs portion here. And xl participates with a coefficient of 4. So this is saying basically this plus 4xl. And here's our less than or equal to the clay supply. And in fact, for this example, we're actually getting another one for free, which we haven't explicitly specified, which is that it has to be greater than or equal to 0 because negative inventory doesn't make any sense. But we could have specified negative infinity for here as well if we chose to. Okay? And we would, of course, do the same exact thing for the glaze constraint here, except the coefficients, instead of being 1 and 4, would be what? 2 and, what was it? 1 and 2. Cool. And then we set the objective. So we define the variables, we've defined the constraints. For optimization problems, we define the objective. And in this case, our objective function is maximize 3xs plus 9xl. You remember that the price of the small vase is $3 and the price of the large vase is $9. So we want to maximize the revenue we get out of that. And this code actually looks very, very similar to the defining constraints. We dereference the objective from the solver. There can be only one, so all we have to do is grab that one. We set the coefficients, so 3xs plus 9xl, and we tell it we want to maximize. At this point, we can tell the solver to go ahead and solve the problem. So we execute the model. This is executing the model right here. The solve method on the solver is actually executing the model. The next few lines of code is just checking to make sure that we got a valid solution. If we didn't, in this case, I'm just throwing an exception saying, yeah, we didn't find an optimal solution. And then finally, we can retrieve the results. Now, by the way, all of this code is on GitHub. The slide at the end will show you where you can actually find working versions of all of these examples for you to go in and play with. And in this case, then, all I'm doing is I'm pulling the solution value out for each of these variables, converting it to an integer, and passing it back in this object. So we define the variables, define the constraints, set the objective, execute the model, and retrieve the results. Pretty much everything you're going to do looks like that. Cool? That's linear programming in a nutshell. So let's build on top of that. Linear programming is really good at solving linear problems, but the world is not a linear place. The world does not always have these full range of values. A lot of times, things are really more integral. I can't sell you 1.5 pots, right? So mixed integer programming is really good for solving problems where we need to do we deal with discrete values. For example, scheduling. And this is, of course, Grace Hopper, creator of COBOL, among other things. Really, without her, we wouldn't probably be using machine-independent programming languages. Another pioneer, another giant in our field. So let's look at scheduling a conference. We're going to schedule talks for a very small conference here. And so we have, what, 4 time slots, 3 rooms, and 10 sessions. And we want to figure out how to schedule these sessions within those 4 time slots and 3 rooms. And the first thing I'm going to do is I'm going to normalize these values. So we're dealing with the IDs of them rather than, we don't care that it's room 125, 128, and 220, or what the actual time slots are as long as they don't overlap. So we're going to normalize those into just IDs, okay? And then we're going to try and set up a model, but we're going to do this with a 2-dimensional model like we did with the linear programming. So if we think of this in terms of each of these variables here, there's 12 variables here, right? 3 rooms, 4 slots leave these 12 variables that we could assign sessions to. And if we think about that as each of those variables holds the ID of the session that it's assigned to, we get a model that looks like this, where our variables are x sub tr. So we have 12 variables, 12 decision variables. Okay? To define the constraints for that, I've kind of identified 3 constraints that we need to have here. It's generally going to be more complicated than that, but let's look at these 3 constraints. Each room time slot combination can have no more than 1 session. Well, we kind of get that for free with this model, right? There's no variable, there's no way to put more than 1 value in there. Each variable can only hold 1 value. So we're okay with that one. Each session must be scheduled exactly once. Okay, well, we can do that with an all different constraint, right? We might have to make a couple of fake sessions here at the end that have no value, and then say each of those 12 variables must be all different. So we cannot schedule 1 session twice. And since there be 12 of them, it means every one of them, in order for them to be all different, every one of them would have to be scheduled exactly once. Okay, so we can define our constraints for that. Here's where we run into troubles with this kind of model. What if sessions 7 and 9 are the same speaker? One speaker cannot speak at the same time. So how do we describe for this model, for the solver, how do we describe that the time slot for session 7 cannot be equal to the time slot for session 9? There's really no way to do that here. In order to do that, we'd have to all right, find where session 7 is, grab the ID of the slot, then compare that to the ID of the slot for session 9. There is no find function in an equation. You can't define an equation that does a search. There's no way to do it. And there are a lot of constraints like this that simply cannot be defined in this type of model where these variables are integer values. Instead, what we do is a model with 3 dimensions or n dimensions. So if we think about this previous model as n minus 1, because we have 3 things, room, slot, and session, and in 2 dimensions, we can think of this as n dimensions because it's a set of variables each for room and slot, and so each variable has its own dimension in the problem. And so what we're seeing here is, you could think about this as a sort of a cube where these tables are stacked one behind each other, okay? So this is the set of variables for session 1. So that first table is all about session 1, and then behind that is all session 2, and behind that all session 3. So you have this 3-dimensional shape, which now contains 120 variables, right? 10 of those tables, one for each session, and 12 variables for each of those sessions, and for each of the room and time slot combinations. And these variables only take Boolean values, 0s and 1s. Now we can describe all of those constraints. So think about that 3-dimensional shape, and let's look at the constraints again. So this is what our variables look like now. So our variable is now x sub trs, so there's 120 of them, and they're Boolean instead of integer. People are taking pictures, so I don't want to jump ahead too fast. All right. Let's look at those constraints again. Each room time slot combination can have no more than one session. Okay, so now this one's a little harder. We don't get this for free anymore. But it's still very easily doable. We can sum for each of the room time. So we're, in this case, think about it as taking one of these cells here and reaching through all 10 sessions. You take those 10 variables. So for each session, that room time slot combination, the sum of those values must be less than or equal to 1. We can't have more than 1. We can have 0 or 1 sessions in that room time slot combination. 0 or 1. We can't have more than 1. So that sum has to be less than or equal to 1. Right? Okay. And we would do that 10 times, of course, or we would do that 12 times, 1 for each. So we would describe that with 12 of those. Each session must be scheduled exactly once. Well, this one's easier to visualize because that's each of these tables. If this is the session 1 table, all we have to do is add up these 12 values here and expect it to be exactly 1. If it's more than 1, that means we tried to schedule it twice. If it's 0, it means we haven't scheduled it at all. So we can constrain that to be exactly 1. Okay. Let's go back to our third one that we couldn't do in the linear model, or in the n-1 model. Time slot for session 7 does not equal the time slot for session 9. Now, hopefully it's recognizable that before you go into this, before you build the model, you're going to know who your speakers are. So you're going to know that this session has this speaker, this session has this speaker, so these two have the same speakers. You're going to know which sessions have the same speaker. So you can define session 7 and session 9 cannot have the same time slot. So now we've got to go through and for each time slot, sum for each of those sessions. Basically, we have to sum for session 7 and session 9. For all the rooms, we have to say, you're basically taking a time slot, session 7, and adding that sum to the sum for session 9. So for this time slot, all the rooms for session 7, this time slot, all the rooms for session 9, less than or equal to 1. So if they're both in the same time slot, you're going to get a 2 there. If neither of them are in that time slot, you're going to get a 0. And if only one of them is in that time slot, you're going to get a 1. That was a little complicated, I realize. It's a little hard to wrap your brain around that, so you might want to review that kind of thing later on. But that's the kind of thing you're going to spend a lot of time doing in these kind of models, is figuring out ways to describe these types of constraints. It's actually a lot of fun. You're solving a puzzle within solving your puzzle. So that's how we do the constraints. How would we do the objective? Well, in this case, we need to create a score that improves the desirability of the solution. Well, what are some of the things that might improve the desirability of this solution? Well, maybe we could include tracks, and we could reduce the number of different rooms in a track. So try and schedule all the tracks in one, each track is all in the same room. Or reduce the number of time slot conflicts between sessions in a track. So you don't have something in the same track going on in 2 places at once. Reduce the total number of steps between the sessions of a track. Now we're getting interesting. Reduce the distance, both in time and rooms, between multi-part sessions. And in fact, maybe multi-part sessions is another constraint, because if you don't want to do part 2 of a session before you do part 1. So we may have to make a constraint that says part 1 of that session must come earlier in time than part 2. And then reducing maybe the number of different days a speaker speaks, or reducing the number of times in a single day a speaker speaks, those kind of optimizations. We'd have to come up with an equation for doing that, and all of that is very, very doable. So here's an example of one of them. Maximize the number of sessions in the same room in a track, where that track is basically sessions 2 and 4. And so what we've done here is we've actually done the same kind of sum as we did for the speaker constraint, picked out for session 2 and session 4, but then we multiplied the sums. And what happens is, if they're in the same room, we're going to get a 1. If they're in different rooms, we're going to get a 0. And we want to maximize that as much as we can. So you have all the mathematical operations at your disposal when you're working with these kind of models. So, what have we done here? We've talked about using artificial intelligences or building them in order to make decisions. And we have this technique, the optimization and search techniques, available to us that we can use to make those kind of decisions, that we can use to build these type of solutions. And these are very efficient if we're dealing with large solution spaces. So the kinds of problems that we can solve with them best are those where there are large solution spaces, and also where we maybe don't have a large corpus of training data to start off with. We're going to use constraints to prune the search space. Linear programming can be used to optimize linear equations, and mixed integer programming to assign discrete values to things like assignment problems. And you'll run into a lot of assignment problems. Here's a bunch of resources. You can contact me this way. These are the code samples. This is where you're going to want to go in and play. If you're interested in dealing with this, you're going to want to go and grab those repositories. There's 2 of them there. The first one, the optimization repository, those are the 3 examples that we just went, or 3 of the examples we just went through. So it's the Sudoku, it's the appetizers example, and the Pottery, the linear programming for the Pottery example. The conference scheduler, this is actually a project my friend Rob Richardson and I are working on. That we don't spend a lot of time on, so when you look at that repo, you won't see a lot of activity on it. But it does have multiple implementations of solvers to schedule it. So you can see this implementation, a Gurobi implementation, as well as a sort of a hard-coded, naive implementation, if you will, to try and solve this very problem. So there's an opportunity there. That's in Rob's GitHub repository. I'm on cognitiveinheritance.com. That's my blog, and I've written a number of articles on this space, and more will be coming, including some summaries of this very talk, probably broken up into multiple articles. I highly recommend this course. If you're interested in doing more in the optimization field, this discrete optimization course on Coursera is tremendous. It's actually, the professor is from the University of Melbourne. He's a blast. He's also Belgian. So it makes for a very, very interesting, he's very excitable too. I loved it. He was very passionate about the subject. Highly recommended. And then these tools at the bottom are the developer.google.com/optimization. That's where you can get the Google OR tools and the documentation for it. The documentation is there. It's lacking in some ways, and it's good in others. But there are explainers in there, and there is a good community around it. So, and they do have examples. Well, they try to have examples in C#, and sometimes they say C# when they actually mean C++, which is really interesting. There's some really good information on the Garobi website. If you're interested in the math behind a lot of how the problems are actually solved, they did a fantastic job of explaining a lot of the details of how they go about doing the solutions or finding the solutions. And then the list of optimization software that I mentioned earlier is there. Cool. So it looks like we've got about 6 minutes left. Are there any questions? Anything I can talk to you or help with? Yes?
I was just interested to watch as you were going through the scheduling problem there, and you were trying to define more constraints like the track one and stuff like that. Instead of adding more dimensions to the set of data of the matrices themselves, you chose to define them as constraints focusing on some of the frames. Does that make sense? So you had, slots, rooms, and then whether the session was in there. You didn't add tracks as another dimension. You added it as an equation.
Right, right.
Is that generally how it goes, or?
Well, if you can reduce the all right, so the question was, why didn't I add tracks as a variable within the solution for scheduling a conference? And basically it comes down to, I wouldn't necessarily add a variable if I didn't have to. So if I can define it in terms of variables that already exist, I'm going to do that generally. You can, so there's some really interesting things you can do. Like sometimes it actually benefits you to have both types of models and actually define constraints in both ways. And you can do that. You can actually have both models in memory at once. You use one as the primary and then can set constraints on the other one that basically drive it to match in terms of that model what the first model is. And then you can set additional constraints on that model. So that can be really interesting, but really complicated at that point. It can get really hard to follow. But yeah, if, I'd be interested in, I hadn't thought about it in those terms because I generally will always automatically default to just defining it in terms of variables I already have if I can. But I wouldn't mind playing. Maybe I'll play with that on the plane on the way home, see how it works out. Other questions? Yes?
Is there any, can you give us any examples of these libraries being used in like commercial situations? Any commercial companies that are using these technologies or these libraries?
Okay, so I can't speak to specifics for NDA reasons, but I can tell you I have an article on cognitive inheritance. Let's see. Let's go to the AI. So this one, AI that can explain why, I'm really talking about, oh, interesting, sorry. Hey, all right. So this article is AI that can explain why. And it uses an example of of an iterative process. So it's sort of a hybrid AI solution where it mixes a combinatorial solution with an iterative process so that you get a process where you can hold the state of things. So you use this to when you reach a solution to a problem, or you can't get a particular solution that you want, you can record the state of the model at that moment, so you can explain why you can't do what you wanted to do. And in doing that, here is an example of the type of problem that I'm actually solving with that, where it's an employee assignment problem. Okay, so employee schedules, and you've got these three pieces. You have the legality of it. What are the legal rules behind whether the employee, how often or how long the employee can work for, versus employees' desired schedules versus what the company needs, levels of coverage and such. And how those come together in a solution. So that's described a little more detail there. That's a very, very common problem. Other problems you'll see are machine allocation problems. They're referred to as knapsack problems, where you've got a certain amount of space and certain, like this machine has this capacity, this machine has this capacity. How can I maximize the, capacity or maximize the revenue or the profit I get by utilizing those machines? Did that answer the question? Gentleman behind you.
So Microsoft has a foundation very similar to this one.
Yes.
So during like 2010 to 2013, something like that.
Yeah.
So it's called the Microsoft Server Foundation.
Yes.
So it's a wrap around all the general, mixing programming engines.
Yep.
And support all these common engines as well. And comes with its own, but you have to pay for that if you want.
Yeah, and that was the part that bugged me about it. So you're talking about the Microsoft Solver Foundation, I believe it's called. And I did play with that a little bit when it came out, but it actually uses Gurobi under the covers, which is the proprietary solution that I was talking about. And ultimately what put me off of it was I didn't have something that I could just get to people for free. And a lot of the software I try to build build open source. I try to build things like the conference scheduler is intended to be for like code camps and those kind of small conferences. So I try to make it so that they don't have to pay for something like that.
The engine itself, you can plug in any line, right? So the open source one is like LP, so that's the free engine can bring, but obviously the performance is not good enough for commercial usage. But like the project I worked before, we bought like IBM C+ engine that worked really well with Server Foundation. But since the team leader left the product, then no one's actually continuing on the future on that. So hence my question was, what's the Google take on that? Like, what's the future of the product?
So I haven't seen any indication of it falling off. I mean, there's not a lot of new commits in the areas of the project that I'm working on. But as far as I know, it's here to stay. It's not anything that they've said we're deprecating this or we're not using it. They use it in a lot of their tooling. So.
The other question is still relevant to my previous one was, so as a very mature product, right? So the way that the language support to define a variable, define a constraint is great. But what about like the toolings around that? So an example is like if as a business manager, business owner, right? If you look at the solutions that it gets from me based on the model I define, is there any way I can say, okay, look, I want to freeze some of the variables, and I'll give that another run. And then the result will give me, the comparison between the two solutions I had, then I, based on, the domain expert, I make a decision on that.
So it is difficult to get information out of these kinds of models. I mean, you have to basically define the model. I think what you're asking me is there ways for me to get more information out of the model to help an expert, a domain expert, kind of use this towards more decision support systems as opposed to artificial intelligences. And certainly you can build the models in ways that provide that kind of information to the users. But you have to program it for that. I mean, most of the time what it's about, and you saw this article here about using a hybrid system to give you more information. Most models are basically a fire and forget type. You throw the data at it, it solves the problem, and it tells you what the answer is, but you really have very little information as to why it got that answer. So if you want more details than that, you have to do something like this, some kind of iterative process where you're snapshotting the information at points in time. Cool. Other questions?